Hello guys, and welcome back to my YouTube channel. In our previous video we discussed the quicksort algorithm, and then we implement the quicksort algorithm using C++, and then we execute our program and sorted this unsorted array in an ascending order. Now in this video we will discuss the concept of heap sort. Heap sort is a comparison based sorting technique based on binary heap data structure. It is somehow similar to selection sort, where we first find the minimum element and place the minimum element at the beginning and repeat the same procedure for remaining elements. Heap sort is a in-place algorithm. It is typically its typical implementation is not stable, but can be made stable, typically 2-3 times slower than well implemented quicksort. The reason for the slowness is a lack of locality of references. Now, advantages of heap sort. First one, we have efficiency. The time required to perform heap sort increase logarithmically, while other algorithm may grow exponentially slow as the number of items of sort increase. This sorting algorithm is very efficient for data, for large range of data. Memory usage is minimal because apart from that is necessary to hold the initial list of items to be sorted. It needs no additional memory space to work. And third, we have simplicity. It is simpler to understand than other equally efficient sorting algorithm because it does not use advanced computer concepts such as recursion. So it is a non-recursive implemented algorithm. Application of heap sort. Heap sort is mainly used in hybrid algorithms like intro sort. The heap sort algorithm has limited uses because quicksort and merge sort are better in practice. Nevertheless, the heap sort structure itself is enormously used. So let's look at some keyword involved with heap sort. First, we have heapify. Heapify is the process of creating a heap data structure from binary tree represented using an array. It is used to create min heap or max heap. Start from the first index of the non-leaf node, whose index is given by n divided by 2 minus 1. Heapify uses recursion. Algorithm for heapify. So we have our heapify function and we passed it an array. Then the root, which is the 0th index of our array or the first index of our array. Largest is equal to the largest function, and we pass our array's 0th index and array's 2 multiplied by 0 plus 1th index divided by array's 2 multiplied by 0 plus 2th index. So if root is not largest, then we swap the root and the largest. Now let's take a look how heapify actually works. So we have this array, unsorted array, and the corresponding binary tree for this array will be this. The task to build a max heap from above array. So first we have the total number of node, which is 11. Then the last node leaf node index 11 by 2 minus 1, and it is 4 last non-leaf nodes. So these are the 4 last non-leaf nodes. Non-leaf mean they have no children. To build a heap, heapify only the nodes 1, 3, 5, 4, 6 in reverse order. So heapify 6, swap 6 with 17. Here heapify 4, we swap 4 with 9, and in heapify 5 we swap 13 with this 5, and heapify 3 we first swap 3 and 17 and then again swap 3 and 15. This 3 and 17, and then 3 and 15. And heapify fun we first swap 1 and 7 and again swap 1 and 15, finally swap 1 and 6. So let's take a look at heap sort algorithm. To solve the problem follows the below idea. First, convert the array into heap data structure using heapify. Then one by one delete the root node of the max heap and replace it with the last node in the heap, and then heapify the root of heap. Repeat this process until the size of heap is greater than 1. So step involved: first we will build a max heap from the input data. At this point the maximum element is stored at the root of the heap. Replace it with the last item of the heap, followed by reducing the size of heap by 1. Finally the heap the root of the tree. Repeat step 2 while the size of heap is greater than 1. Now let's take a look at working of heap. To understand heap sort more clearly, let's take an unsorted array and try to sort it using heap sort. So consider we have an array of 4, 10, 3, 5 and 1. We will build a complete binary tree from this. So this at first step we create a binary tree from this array. Then transform into a max heap. After that the task is to construct a tree from that unsorted array and try to convert it into a max heap. To transform heap into a max heap, the parent node should always be greater than or equal to the child node. Here is the this example. As the parent node 4 is smaller than the child node 10, this parent node is less than this child node 10. Thus we will swap them to build a max heap. Transform it into a max heap. So after converting our binary tree into a max heap, the 4 less than 5 and 5 is greater between the two children. So this is now our max heap. Here the parent node is greater than all of its child nodes, and now our array is something like that: 10, 5, 3, 4, 1. First 10, then 5, then 3, then 4, then 1. So this is our array of our this max heap. After successfully converting our array into a max heap, we will perform heap sort. Remove the maximum element in each step, move it to the end position and remove that, and then consider the remaining element and transform it into a max heap. Then delete the root node 10 from the max heap. In order to delete this node, try to swap it with the last node. In this example the last node is 1. After removing the root element, again heapify it to convert into a max heap. The resulted heap array should be something like that. After we remove the max heap and replace it with the leaf node, now our array is something like this. And after heapifying it, it will convert into this. Then we repeat the above step, that it will look like the following. So now we have 1, 4 and 3, 1, 4, 3, 5. Then we remove the max element from our heap. Now we will remove the root in this example 3 again and perform the heapify. And after removing the max, our array will be something like this. Now let's try to implement this heap sort in C++. First let me remove the code of our previous example of quick sort. First I will write our heap sort function. Now for code for our build heap, I will use for loop. Int I is equal to n divided by 2 minus 1. And then our I greater than or equal to 0, and then increment of I minus minus. Now I will call my heapify function and will pass it an array, size of array, and an I. Now we have not made our heapify function yet, but I will create it after this heap sort function. Next again our for loop, and this time our integer will be equal to n minus 1 and condition will be I greater than 0, and then the decrement I minus minus. Now I will call our swap function. Now after the swap function call, I will call my heapify function again and will pass it my array and the ith and then 0. So our heap sort function is ready. In next video we will create our heapify, swap and print array function, and then we will test our program. Hello guys, and welcome back to my YouTube channel. In our previous video we saw definition of insertion sort and then see an diagram of how we can achieve insertion sort, and then we implement insertion sort using linked list. After that we saw the time complexity and space complexity of insertion sort. So in today's video we will see merge sort. So let's get into it. The merge sort algorithm is a sorting algorithm that is based on divide and conquer strategy. This divide and conquer strategy is very good strategy when you want to reduce the time complexity of an algorithm. Binary search tree also use this divide and conquer approach for sorting things. In this algorithm, the array is initially divided into two equal halves and they are combined in a sorted manner. Merge sort working process. Think of it as a recursive algorithm continuously splitting the array into half unit. It cannot be further divided. This means that if the array become empty or has only one element left, the dividing will stop. In the base case, to stop the recursion, if the array has multiple elements, split the array into halves and recursively invoke the merge sort on each of the half. Finally, when both the halves are sorted, the merge operation is applied. Merge operation is the process of taking two smaller sorted array and combining them into eventually longer array. So now let's take a look at the illustration. To know the functioning of merge sort, let's consider an array of 38, 27, 43, 3, 9, 82 and 10. At first check if the left index of array is less than the right index. If yes, then calculate the midpoint. Here we consider I as the left index and R as the right index. So if I mean left index is less than R, then we will calculate it midpoint. Now as we already know that merge sort first divides the whole array iteratively into equal halves unless the atomic values are achieved, mean unless only one element is remained in the array. Here we see that an array of 7 items is divided into two arrays of size 4 and 3 respectively. Now again find the left index. Now again find that is left index is less than the right index for both array. If found yes, then again calculate the midpoint for both the arrays. So in this case our midpoint will be this between 3 and 9, and it will divide this array into two. Now further divide these two arrays into fourth halves until the atomic unit of array is reached and further division is not possible. So we will keep dividing this array like this, and after that we will again until these atomic value mean only one element is left in each cell is achieved. After dividing the array into smallest unit, start merging the element again based on comparison of size of the element. First compare the element for each list and then combine them into another list in a sorted manner like this. After the final merging, the list look like this. So we have this 27 and 38 on left side, and then right side we have 3 and 43. When we will merge it in an ascending order. So 3 come first, followed by 27, then 38, then 43, and same goes for these two. First 10, first 9, then 10, then 82. Now after this merge is complete, now it's time for the merge of these two subarrays. So we will also merge them via comparing in a ascending order. So 3, 9, 10, 27, 38, 43, and then 82. Now this following diagram shows the complete merge sort process for example for an array of these 9 elements. If we take a closer look at the diagram, we can see that the array is recursively dividing into 2 halves till the size become 1. Once the size become 1, the merge process comes into the action and start merging the arrays back till the complete array is merged. So these numbers indicate that the order in which the step is processed. So at the first we divide our first array into 2 halves, and then we keep on doing that until we achieve this atomic value level. After achieving this atomic value level, we start to merge these arrays in an ascending order manner. So now it's time for our algorithm for the merge sort. So at step 1 we start our program. Step 2 we declare array and left and right and the mid variables. So basically we will be declaring 3 variables, left, right, and mid variable. At step 3 we perform the merge function. If left is greater than right, then return. Then we will define our mid, left plus right divided by 2, and then the merge sort algorithm, we will pass it array, left, and mid, and then again merge sort function, and we will pass it array, then mid plus 1 and the right, and then we will call our main merge function, and then our function will be stopped and our array will be sorted using merge sort algorithm. So let's start the program for our merge sort algorithm. It will be a bit more complex than all the previous sorting algorithm that we have seen so far. So first I will write our function of merge. It will be of void type void merge. Then it will accept for, or let me first define our function of merge sort, because we will be calling our function merge from the merge sort function. So first merge sort, it will be easy for you to understand. So first will come our merge sort. It will accept 3 parameter, an integer type array, then a constant begin, then our const of end. if the begin is greater than or equal to the end, then we will simply return. It will be a recursive return. After that, we will define our mid. It will be begin plus and minus begin and divided by 2. After that, we will call our merge sort again and we'll pass it our array. Array begin and mid. After that, we call our merge sort again and we'll pass it our array mid plus 1 and end. Array mid plus 1 and our end. After that, we will finally call our main merge algorithm or merge function, and we'll pass it our array begin mid and end. So now it is showing us that merge is not defined because we still have not defined our merge function. So let's define our merge function on the top of our merge sort function. It will be a void type of function. It will accept an array, then integer const left, then an integer const mid, and after that an integer type of constant variable right. So now here we will define our sub array. It will be a auto const sub array 1, it will be equal to mid minus left plus 1. Now our auto const sub array 2, it will be equal to right minus mid. Now we will create our temporary array. Array 1, now our right array, it will be equal to a new integer type of array 2. Now we will copy data to our temporary arrays left array. And the right temporary array. We will be using our for loop where we will be define auto I is equal to 0 and I less than sub array 1 and increment I by 1. So inside of the body of our for loop we'll define our left array ith index equal to our array left plus I index. So that's all from today's video. The video is already got much bigger. We will continue our this code of merge sort algorithm in C++ in our next video. Till then, take care. Hello guys, and welcome back to my YouTube channel. In our previous video we discussed the recursive method of implementing the insertion sort in C++. So we make this insert sort recursive function and we define our base case, and then we test this program, and it was a successful execution. Our array was sorted indeed. And for now, this video we will be discussing a bit more important and a little complex topic, which is radius sort. The lower bound for the comparison based sorting algorithm, for example merge sort, heap sort, quick sort, is n log n. They cannot do better than n log n. And on the other hand, counting sort is a linear time sorting algorithm that sort on omega n plus k time when elements are in the range of 1 to k. What if the elements are in a range of 1 to n square? We can't use counting sort because counting sort will take omega n square, which is the worst case comparison based sorting algorithm. Can we sort such an array in linear time? Yes, indeed, radius sort is the answer. The idea of radius sort is to do digit by digit sort, starting from the least significant digit to the most significant digit. Radius sort uses counting sort as subroutine to sort. Radius sort algorithm. Do the following for each digit I, where I varies from the least significant digit to the most significant digit. Here we will be sorting the input array using counting sort or any other stable sort. So according to the ith digit. For example, the original unsorted list is 170, 45, 75, 90, 802, 24, 2 and 66. Sorting by least significant digit one's place gives. Note that we keep 802 before 2 because 802 occurred before 2 in the original list. The similarity for pairs 170 and 90 and 45 and 75. So the 170 0, 90, 802, 2, 24, 45, 75, 66. Sorting by next digit tens place gives 802, 224, 45, 66, 170, 75 and 90. Sorting by the most significant digit 100 place give us 2, 24, 45, 66, 75, 90, 170 and 802. So all of them are now sorted in ascending order. So what is the running time of radix sort? Let there be a d digit in input integer. Radix sort O into d into n plus b time, where b is the base for representing numbers. For example, for the decimal system b is 10. What is the value of d? If the k is the maximum possible value, then d would be the O into log b into k. So overall time complexity is O into n plus b multiplied by log b into k, which looks more than the time complexity of comparison based sorting algorithms for a large k. Let us first limit k. Let k is greater than or equal to n की power c, nth power c, where c is the constant. In this case the complexity become O into n log b into n, but it still doesn't beat comparison based sorting algorithm. What if we make the value of b larger? What would be the value of b to make a time complexity linear? If we set b as n, we get the time complexity as omega n. In other words, we can sort an array of integer with the range from 1 to nth power c if the number are represented in base n, or every digit takes log to n bits. So now let's see the application of radix sort. In a typical computer, which is sequentially random access machine, where the records are keyed by multiple field, radix sort is used. For example, you want to sort 3 keys month, days and year. You could compare 2 record on year, then on a tie on month, and finally one on the date. Alternatively, sorting the data 3 times using radix sort, first on the date, then on month, and then finally on calendar would be used. It was used in card sorting machine with 80 columns, and in each column the machine could punch a hole only in 12 places. The sorted was then programmed to sort the card depending upon which place the card had been punched. This was then used by operator to collect the card which had the first row punched, followed by the second row, and so on. Now, is radix sort preferable to comparison based sort algorithm like quick sort? If we have log to n bit for every digit, the running time of radix appear to be better than quick sort for a wide range of input numbers. The constant factor hidden in asymptotic notation are higher for radix sort. The quick sort uses hardware cache more efficiently. Also, radix sort uses counting sort as an subroutine, and counting sort takes extra space to sort a number. Now the key point about radix sort. Some key point about radix sorts are given here. First one, it makes assumption about the data, like the data must be between a range of elements. Input array must have element with the same radix and width. Radix sort works on sorting based on individual digit or letter position. Next we must start sorting from rightmost position and use a stable algorithm at each position. Now radix sort is not an in-place algorithm as it chooses a temporary count array. So now let us implement the radix sort algorithm in C++. So So now I will move to my code editor, clear the previous code. So now let me first write a function for getting the maximum value from an array. It will be a utility code, so I will name it as getMax. It will accept an array and the size of array. Now we will use a for loop. Int I is equal to 1 and I is less than n and I plus plus. Now we will check if the arith I is greater than max, then we will initialize mx to that index the array value, and we will simply return the max. So this is a utility code for returning the maximum value from an array. Now we will write our function for count sort algorithm. I will name it as count sort. It will accept an array, an integer n, and an integer exp. Now here we will define an integer of output. Now our first for loop second for loop I is equal to n minus 1 and I is greater than equal to 0 and I minus minus. our radical sort function. Now our void print function. Now our main driver code, an integer type of array having values 170, 45, 75, 90, 802, 24 to 66. We will call our radical sort and we will pass it our array and n, and then our print function and will pass it our array and n. Now let's try to run this program. It is showing some errors. Let me just quickly check them. So yeah, our array is sorted now using the radical sort method. So that's all from today's tutorial. Thanks for watching, and don't forget to like, share and subscribe our channel. Hello guys, and welcome back to my YouTube channel. In our previous video we discussed the heap sort algorithm and we write some code of our heap sort algorithm. So let's continue from our previous video. We have written our heap sort function. Now let's write our heapify function. Now we will initialize the largest element as root. Now we will check if L is less than n and the lth index of array is greater than the largest index of our array. will call our swap function again. And after the swap function we will recursively call our heapify function. So now let's write the code for our print array function. Now let's write our main drivers code, main function code. We will first create an array and give it the value of 12, 11, 13, 5, 6, 7 and the size of array Now we will call our heap sort function and we will pass it the value of our array and our length. Now our print array function. Now let's try to run our program. So you can see our sorted array is 5, 6, 7, 11, 12, 13. So we have successfully sorted our unsorted array using the heap sort method. Now let's take a look at the time complexity of using heap sort method. The time complexity of heap sort method is O log n, and the space complexity is O of 1. So now let's also see some interview question relating heap sort. So first one is, what are the two phases of heap sort? The heap sort algorithm consists of two phases. In the first phase, the array is converted into a max heap, and in the second phase, the highest element is removed, i.e. the one at the tree root or the parent root, and then the remaining elements are used to create a new max heap. So our next question is, why heap sort is not stable? Heap sort algorithm is not a stable algorithm because this algorithm is not stable because operations that are performed in the heap can change the relative order of equivalent keys. Next question is, heap sort an example of defined and conqueror algorithm. So heap sort is not at all a divide and conquer algorithm. It uses a heap data structure to efficiently sort its element and not a divide and conquer approach to sort the element. Our next question is, which sorting algorithm is better, heap sort or merge sort? The answer lies in comparison of their time complexities and space requirement. The merge sort is slightly faster than the heap sort, but not other but on the other hand, merge sort take extra space. Depending on the requirement, one should choose which one to use. Next we have why heap sort better than selection sort. So heap sort is similar to selection sort but with a better way to get the maximum element. It takes advantage of heap sort data structure and get maximum element in constant time. So now let's start our next sorting algorithm, which is counting sort algorithm. Counting sort is a sorting technique based on key between a specific range. It works by counting the number of objects having distinct keys value, a kind of hashing. Then do some arithmetic operation to calculate the position of each object in the output sequence. Some characteristics of counting sort. Counting sort make assumption about the data. For example, it assumes that value are going to be in the range of 0 to 10 or 10 to 99. Some other assumption counting sort makes is input data will be all real numbers. Like other algorithms, this sorting algorithm is not comparison based algorithm. It hashes the value in a temporary count array and uses them for sorting. It uses a temporary array, making it non-in-place algorithm. Now we will take a look at an example of counting sort algorithm. For simplicity, consider the data in the range of 0 to 9. So we have our input data 1 4 1 2 7 5 2. Take a count array to store the count of each unique object. Follow the below illustration for better understanding of counting sort algorithm. The illustration is, for simplicity, we have this data from 0 to 9 range and its indexes are all 0. Count each element in the given array and place the count at the appropriate index. Now store the count of each unique element in the count array. If an element repeats itself, simply increase the count. So for example, this one appears 2 times, so we increase its count by 1 and now its count is 2. Here the count of each unique element is the count array as shown in below. So we have 0 0, so the indexes are 0 1 0 to 9. And we have our count of 0 2 2 0 1 1 0 1 0 0. For simplicity, consider this data range and their indexes are 0 1 2 3 4 5 6 7 8 9 and their count array is given below 0 2 2 0 1 1 0 1 0 0. Modify the count array by adding the previous counts. So modify the count array such that each element at each index store the sum of previous count. So for example, in case of this indexes, the modified count array indicates the position of each object in the output sequence. Find the index of each element of the original array in the count array. This gives the commutative count, like this, and then we have this 4 plus 0. So rotate the array clockwise for 1 time, then we will have our count of 0 0 2 4 4 5 6 6 7 7. Output each object from the input sequence followed by increasing its count by 1. Processes that input data 1 4 1 2 7 5 2. The position of 1 is now 0. Put data 1 at index 0. Increase a count by 1 to place next data 1 at an index 1 greater than this index. So we will keep doing this until our array is sorted. So now we will try to implement this code in C++. So let me clear all of our previous code. And let me include 2 more libraries. Bits over std C++.header, and we will perform this sorting operation on a string. So I will include the string.header class too. Let me define the range to 55. Now let's write our count sort method. Void sort, it will accept a character type of array. Next, our integer count, it will be the range plus 1 and our I. Now I think this video is already got very lengthy. We will continue this code from our next video. Till then, take care and stay tuned for the second part of this video. Hello guys, and welcome back to my YouTube channel. In our previous video, we were discussing the concept of merge sort. We saw what is the merge sort, and then see the pseudocode or algorithm for merge sort, and then we finally implement merge sort using C++. Now in this tutorial we will see quick sort. So like merge sort, quick sort is also a divide and conquer algorithm. It picks an element as pivot and partition the given array around the pivot. There are different versions of quick sort that pick pivot in different ways. So we can have always pick the first element as pivot, then we can achieve merge sort by always picking the last element as pivot, then we have the random element as pivot, and then pick the median as pivot. The key process in quick sort is partition function. In merge sort it was merge, but in quick sort is partition method. The target of partition is given an array and an element x of an array as pivot. Put x at the correct position in the sorted array and pull all smaller elements. Smaller than x means smaller than our pivot. Therefore x and put all greater element greater than x after x. All this should be done in a linear time. So for example, we have this array of 10, 80, 30, 90, 40 and 70, and we pick 70 as our pivot point. Now it will make a structure, tree like structure. Now all the elements which are less than 70 will be placed at the left side, and all the elements which are greater than 70 will be placed at the right side. So for example this. So after the first partition we will get this. Now again we will choose and pivot from these subtrees. In this case we choose 50. Then again all the elements less than 50 will become on left and greater than 50 will become on right, and in this case right tree is empty. And same for our right partition, element greater than 80 will become at right subtree. Now after the second partition we have a structure like this. Now we again do the partition, and this time we choose 40 as pivot. Now 13 and 10 will become will be placed on the left side because they are smaller than 40, and the right side is empty because there is no element greater than 40, and so on it will be going until we achieve atomic values. Now let's take a look at our partitioning algorithm. There can be many ways to do partition. So the following pseudocode adopt the method given in this curly CLRS book. The logic is simple. We start from the leftmost element and keep track of the index of smaller or equal to element as I while traversing. If we find a smaller element, we swap the current element of array's ith index, otherwise we ignore the current element. So the pseudocode for recursive quicksort function is here. So we have our quicksort function. It accepts an array, a low and a high, total 3 parameter. If low is less than high, then the partitioning index pi of array is now at right place. So the pi is equal to partition, and then we give it an array low and high. It is a recursive. Then we do a recursive call before the pi and after the pi. Now the pseudocode for partition. The function takes last element in pivot, place the pivot element at its correct position in sorted array, and place all smaller than the pivot to left of pivot and all greater element to the right of pivot. So our partition function will accept 3 argument array low and high. Then the element to be placed in the right position pivot will be equal to array's high, and then I is equal to low minus 1. So it is the index of smaller element and indicates the right position of pivot found so far. Then we will run our for loop, in which we will initialize j equal to low, and the condition will be the loop will keep running until j is less than or equal to high minus 1 and the j increment. So inside of this for loop we will check if jth index of array is less than pivot, then we will increment I by 1, and then we will swap the ith array and the jth array index. So now let's take a look at the illustration of partition function. Consider we have this array 10, 80, 30, 90, 40, 50 and 70. So the indexes are 0, 1, 2, 3, 4, 5 and 6, and the low is equal to 0, which is this, and the high is equal to 6, which is the last index, and pivot in this case we choose 70, the last index element. So initialize the index of smaller element I is equal to minus 1. So our pivot is 70 and our counter variable I is the index of smallest element and j the loop of variable. We start the loop with initial values. Then our test condition is jth index of array must be less than or equal to pivot, and the value of variable I is equal to minus 1 and j is equal to 0. So traverse element from j is equal to low to high minus 1. J is equal to 0 since jth index of array is less than or equal to pivot. So do I plus plus and swap these two values. Now we also create and swap function. So you can see all of this illustration for the merge sort as for quick sort algorithm. Now we will write our code of C++ for the implementation of quicksort algorithm. So let me clear all of our previous code of merge sort algorithm. First I will write our swap function. Now time for our partition function. It will be of an integer type and accept an array. A int low and a int high. Then our pivot will be equal to the height array, index of our array, and int I is equal to low minus 1. Now our for loop. I minus 1 and j plus plus. We'll call our swap function. Now here our swap function, and I will pass the I plus 1 index of our array and array's height index. And then our return, which will be I plus 1. Now our quick sort algorithm function call. Low is less than high, then we will create our pi. And then again our quick sort recursive calls, array, low and high, and then our high. Now our int function call. Now our main dragger program, we will create an array of integer and initialize its values to the 10, 7, 8, 9, 1, 5, and we'll give it this. Size will be 5. Then we simply call our quick sort function and give it our array, then our n and n minus 1. Now simply print our array. So now let's call our run our program. So you can see our array is now sorted. So this was a successful implementation of quick sort in C++. So that's all from today's video.